Thanks again, Donna. I gave this talk a while ago to ASCG, actually, and had a small criticism that I'd put on a disclaimer at the beginning that said, what I'm going to say is probably not all the truth. And I'll put the same disclaimer on as all our financial people do, that a lot of the stuff here is opinions, and the interpretations we do, an opinion, the inversions we do, an opinion. But I put on the bottom here, the only thing we know about inversion, even if it's 100% fit, it must be wrong because there's error in the data. So anyway, it was supposed to be a light-hearted start to the talk. Pity there'll be some other poor attempts at humor as well, I think. Anyway, the way I'm going to break the talk up is, I was expecting to see a lot younger people here that can't remember back 10 years when it's been just about to the day that the first holes went through nickel sulfides at Nova. And I'll just have a quick rehab of Sirius Resources press releases and Mines and Money, and that is where I've drawn a bit of the information from. And I'll probably dwell a bit long on the initial EM and all the different varieties of EM that we did throughout the process of exploring and sterilizing, for a better word, the whole licenses. And then we carried out lots of other geophysics there as a characterization and to see what could be used for finding this particular style of deposit. I presented a bit of a conclusion at the end. Conclusion's more my opinion than anything else. See if I can get the arrow to go the right way. The background picture's got nothing to do with. Anyway. Oh yeah, before we start, it's always important. There's lots of people involved in these discoveries, and the Sirius Resources management. And John Bartlett, who was on the ground at Marcus. And the ASX, because that's where I've drawn on a lot of the beginning parts, and the team at New Exco, who's quite varied, and quite a number of geophysicists and geologists willing to work. Oops, wrong button. Here we go. And Jem, who did the original IP, and as I said in Donna's thing, I have quite a respect for the guys in the field. Hainsey on the gravity, of course, Vortex and Search, Gap, Merlin, and Gallagher, and the IGO, of course, who's there. And I think Lady Luck needs to be acknowledged, and some good judgment from the management team, and hopefully from the geophysics consultancy as well. And this is often, people go looking for some type of deposit and find something else. This is an early press release from Sirius, and they had in their back of their minds that intrusive hosted nickel is a pretty good place to be, and that Fraser Range had been explored before Kambolga, and I think it was the intrusive nickel was the main target before the nickel boom, and then we found the komatiite type, which took our focus away from these big intrusives. This is how Sirius was spooking, looking for intrusive nickel, and I think they were actually hoping to be in this top quarter. This is a log. So for those that are shy of mathematics, this is a log thing, and you can get from not much to very big numbers across this graph. We happen to be jammed in on the left-hand side, which is probably okay. And actually, with the things, New Mexico has actually been involved with quite a few of these red spots, if you look through there, from our old Mr. Woodhouse, who worked on Mount Keith and Perseverance. He was actually Rocky's boss when Rocky's was found. So we've got quite a think that was my spooking for the day. So we've got Nova sitting, intrusive nickel sitting up pretty well. I'm sure they would have preferred to see it in these larger camp areas, and I suppose we're still going to wait for more to be found in the Fraser Range. I'm sure it will be put on there as a diamond one day, not just a lone deposit. Okay, so they're looking for intrusive nickel and went to government maps, which we've got to take a lot of credit. And here we can see quite we shouldn't do that, linear, this Albany Fraser orogeny, and you can see how it's developing there, all quite linear and long looking, and then we come up here onto from less dense to quite dense rocks and probably a bit less cover and magnetic units. And somebody there had spotted something that's a little bit more non-linear and interpreted as, we don't know, a dome, a plug, layered intrusions, unexplored area. And it had a real kicker, nickel and copper of reasonable numbers. So hence the tenements. And a bit more exploration, and I think they're probably in a way, how to tackle that. And I would say that the question was, well, we'll just do a little bit more soil geochemistry, have a kick around on the ground, see if we can demonstrate these are actually good mafics and mineralized. And geochem survey, actually soils. You can, not lucky I'm not driving the car. Okay, back again. All right, good stuff here. We've got a nice big geochem anomaly that's sitting internal to this eye-like feature that's obviously magnetic and 2 kilometers. It's got some good nickel and copper geochem. They went on. I was just going to say that the nickel and the copper is only in the weathered zone on the surface. They got into some mafics and ultramafics, which returned some. This is the better one here. This stuff on the bottom, even if that is probably a little bit hard for your handheld lens to look at, there is some pentlandite and in there, which is always a good sign when you're looking for nickel and copper. The numbers that they had before, so I went past that too fast, is 600 odd nickel and 400 copper, which is getting interesting. Out with a RC rig and define a blanket, but not much in the basement. So that's when they came to us and said, well, what will we do? And if you come to a geophysicist or an army person, they like to say, well, we'll declare war, or we'll probably do some geophysics. But they didn't have a big budget to go on, so now came this is just some standard vanilla flavored EM, 200 meter loops, 400 meter lines in loop. We didn't suspect that we're going to be getting any spurious effects. At the moment, you see a lot of people doing sling ram and all sorts of other stuff. We didn't have those problems. We had the biggest problem was a small budget and a moderate area to cover. You can see by that how tight we were with the infill, 400 meter line spacing, a little tickle here and a bit of infill. Obviously got it wrong there, didn't go far enough that way to pick these conductors up. This was a fabulous conductor with a good time constant. Paleo channels thickening to the south here, as you can see these response coming up, and 3 conductors, low time constants, and as higher time constant as we could really define with the 1 Hertz work that we're looking at. This little arrow here points at 9,800 north, and we'll later on, when I'm going to get into the itty-gritty and get some cross sections to look at, and we'll be generally looking at this cross section here. That's 9.5, 9.6, 9.6 north. How did that compare with the geochem that we had? Here is that was the first plate models that we came up with, and they stood the test of time. Even with all the work, they didn't move very much at all. You can see in white here, that was the first modeling. There's 5 small plates that take us down quite a long way, actually, a kilometre. Pity we didn't get that full strike extent, but that was probably for the optimists. Anyway, geochem, good conductor. Hard argument not to do a little bit more drilling. These other conductors were lower time constants and probably out of that geochem's influence, so became a lot lower rated. So that was all pretty excited. First drill holes. This is section 9,500 north. It's where the shallowest part of the conductor. This one here is a little bit misleading. Where's the pointer? This is the deep end, so this is a long way under. When I look at this, I see it plunging to the left, but this is actually plunging to the right and to the north. And this is where we drilled here on the first sector. And it's quite interesting to see the numbers. And you have to just picture in your mind, if you're the geologist out on the rig, and if you drilled, I can't read the number, 25, I think it is, first, and went through some irony, conductive sort of shit, what you would be thinking about. But anyway, they had a good geophysicist who said, we're going to drill here. And that was 4 meters at 4 or something like that. Then they moved up 24. Did they go 25 and then 26 and hit it again? Anyway, that was the fabulous fabulous day. I remember Mark Bennett phoned me up and said, we hit the target, and it was 2 meters out. And I said, your hole must have dropped. And he said it did. It did. So that was really, that's the main part of the story. For the geophysicists in the audience, and there are some that I can recognize, here's the initial profiles, 3-component, fluxgate working away quite nicely, and classic twin peaked anomaly, and that black part there, and you see these plates will stay the same through the whole presentation that we used on it. We didn't have Bollinger in there, but you can see Bollinger just trying, and we'll see that gets a little bit stronger later on. Not a lot of cover conditions here, which is probably strange for Fraser Range. Oh, I haven't. Oh, I pressed this bottom one. Oh, good work. Back off again. Okay, here we go. So we've made a discovery, and now we've actually got to drill it out. And we need to know how big is this, how far does it plunge down, and how do we tackle that? And we actually did this with, or tried to do it with a series of fixed loops. These plates that you're looking at there are the ones that we've seen all along. And the model that you see there is from our initial plate after we went and measured these fixed loops. And you can see these two fixed loops that we set out, well coupled with the perceived position of the target, and we chased it further to the north. This top line's 8150, which is obviously 650 meters past 9.5. So that's at 600 or 700 meters. And we came up with, we think we're getting an end to it with the Y component helping us. And that actually has proved to be exactly where it was. We wanted to develop an extra method of exploring through the district, and we're coming to the limit of the flux gate's precision in the data that we were using. So we changed to a different style of instrument that could go to very low frequency and work quite quickly. And this is a Samson probe, and it's less affected by wind noise, and it's quite good. This is taken at 8-second cycles. Steve, that's better. Thought you're asleep. No. I'm sorry. Anyway, this is taken at very low frequency. It's a cesium vapor magnetometer that's used, I think, and it only takes total field, but quite good with a fixed loop. Let's put out the loop sitting in here, and we ran this line over the top. And you can see it quite, that crossover here is the top of Nova, and this extra bulge here happens to be sourced by the flat-lying Bollinger deposit. Because we've measured for such a long period, we can then get a good estimate of its real time constant. And I believe time constant, which is of interest to the geophysicists, that the time constant of Nova Bollinger is in excess of 800 milliseconds. And I think that's probably even underestimating it. So it's a very conductive target, and that actually makes it, a kicker to that is that it doesn't respond well to high frequency impulses. From that stage, we decided that's a good way to explore, and with very cooperative and generous clients, GAP geophysicists carried out a large number of loops and stations. You can see them sitting there on top of the geology that we've got there with the magnetics in the background, and we covered everywhere. Fantastic. One could ask, did we find anything else? There were a couple of conductors that were targeted, and we came up with conductive material on there. I think this geology had been compiled from all the drilling that had been done. And this is my favorite slide of all. It was quite an eye-opener to me, and hopefully to the other geophysicists here. We're in this quite resistive terrain, sort of like Canada, that we saw in the first targeting. This loop happens to be well over a kilometre. I can't read the numbers. I think it was 1,500 meters away from the target. This is what you would consider about as bad coupling as you could ever get, and we still get a weak response. This is from 200 through to 1,700 milliseconds. It's plotted up there. You can see very little background response, even in the middle of the loop. You'd expect in the middle of quite a powerful loop. This is 160 amps, I think we're using in this loop, and very little spurious responses in there. No real background responses once we're away from the loop, and we're seeing a target out there. That is quite an eye-opener to me. Okay, that's sort of the end of the EM monologue. And I'll probably go a little bit quicker through the other stuff that was other geophysical work that we did. And I've presented in two ways. One's with straight sections that people like my learned friend like to see, of just straight profiles, and the others are for some inversions. As a presentation for the geologists, we did IP over the. I shuffled around. Okay, we did IP over the area. If you can picture what we've been looking at, that's the same sort of thing. There's 400 meter line spacing. I think they're reading down as much as they could. Dipole, 100 meter dipoles, and I think we're getting down to N of 11 in some, or in most places. Search did the first couple, and Vortex finished the job off. The one on the left is the IP section. You can see the plate here, which is where Nova and Bollinger is located on both of those things, both of those plots. There's a lot of matrix and disseminated sulfides coming out above and proximal to the massive sulfides there. So the IP was a logical way to look at the look to see if we could find any more of that in the district or on the lease. What you can see here, which is quite amazing, on the resistivity sections on the left, right, sorry, you can see the overburden paleo channel getting thicker. You can see this thing sitting in here, which is a low resistivity, a conductive material. That's on line 9.5. And then you can see around those other two conductors, little bit, but in the other side, you can see it's got chargeable. There's a lot of disseminated sulfides around those other two conductors that we'd picked out. And you could argue there is I think I've shuffled these guys around a bit. Sorry to say, that's the one that we wanted to look at. This is 9.5 north with some ground magnetics and some gravity on board, you can see. And the top one is apparent resistivity, and then you've got apparent chargeability below that at our normal Newmont times, and the wireframe that we've been looking at sitting below there. For your old-fashioned geophysicist that looks at these sections, he can see that this is going background response of very little chargeabilities. This is Newmont times at 2s and 3 millivolts per volt or seconds, and these are jumping up to 20s in here. It's millivolts per volt, so quite chargeable, and the apparent resistivities are down well below 1 ohm meter, up to a couple of 100 ohm meters where it's blue. So you can see the surface coverage, these classic pant legs appearing in here. So there's some chargeable material kicking around, and right over to the east, that was the second conductor that ended up being a bit chargeable as well. So the IP is actually picking it up in a reasonable manner. We'll look later and see where these magnetic source lies, but they certainly look coincident when we're looking at this, and a wee bit of gravity. There's quite a bit of gradient there. This is only a couple of milligauss right across the whole tenement, and they're sort of varying. I think that's their 0.2s, so it's not a big thing. Denser rocks probably sitting, or shallower rocks sitting in here. I want to go back. We took the both the magnetics and the gravity, and ran various types of inversions on them for comparison. And this was what seemed to be one with a reasonable geological reasonable geological content in the inversion. And we can see here this density on the, so the density one's on the left and the magnetic susceptibility is on the right. And we've got this grav anomaly that we looked at before, which is about 0.2 or 0.3 of a milligal, and that's where that's exactly where Nova Bollinger would or Nova would daylight. So I now need to go and find. Okay, this is that's to put us in perspective. That's the line that we'll be talking about. So, okay, in modern talk, this is how we've been looking at the inversion results. These are that section that we just looked at, and which we can see on the surface here. This is magnetic image, apparent resistivity inversion, which is just sitting underneath there, and that's that section there, and the wireframe. So it's near coincident, but not quite. The one in the south, you can see this little bulge there is that grav anomaly. This is the grav image over the top. Resistivity again, and with the bottom sector is the magnetic susceptibility inversion shells. So we can compare them all with the low resistivity inversion. So there's some coincidence there, whether you believe it's exactly the same thing or not. My interpretation of the pseudo sections would have them being coincident, and I wouldn't have put it where the inversion did, but I think that's probably better at it than I am. Similar for the chargeabilities inversion. I know it looks similar, but you get that. That's where the main chargeability zone is, and that happens to be also quite magnetic. This isn't taking into consideration remnant magnetization, but what it does show is above Bollinger was quite a lot of disseminated and matrix ore. And I think the IP had picked that up. You could ask, did we do much more IP after this slot? And the answer is not a lot. We also, Shane was traveling across the country, and he stopped off with his MT system, and we did a quick profile across. That's the 9.6 right across the top of the 9.6 line. There's the wireframes that we were looking at before, and these are induction vectors from the MT. And you could say, well, if it's this system, it's not going to pick up something like Bollinger. It's not going to do much at all. Anyway, I was quite surprised to see these induction vectors are supposed to point at your conductor. These are 100-meter stations across here for about 1.5 kilometers across the top of it. And these guys are actually pointing at Nova Bollinger. This is reasonably high frequency stuff. That's 100 hertz there. I think. Okay. These are my opinions, of course. So this highly conductive massive sulfides in reasonably resistive terrain, that TEM is a very powerful tool. What I haven't shown is all the downhole work that we've done, and we could show with the downhole that we can see Bollinger at 500 meters on a kilometer hole, quite a long distance off. Although the IPs picked up quite a lot of geological noise, and I still think it's a good tool in the proper hands, and if we use it in a detailed manner, we would have drilled Bollinger from and Nova from that. And even the AMT picked it up, but I probably wouldn't be picking that as a routine exploration tool. This is our friend John Bartlett with the hole here. And that's the end. Winners are winners.